Hello everyone. In this video, I want to talk about a ball bearing assembly in SolidWorks. So I've seen some videos on the internet, on YouTube, from some of the even well-known CAD channels. And when I found that the way they are putting the mate, I found they have a mistake about the cage, and I wanted to clarify that. So if you look, the way I mated it is, first, I basically force the inner ring to be concentric with the outer ring and their faces to be flush or coincident. They are the same width. Then I made, this is the part that you need to do, I made the surface of the ball tangent with the slot in the inner ring or the raceway, and with the same on the outer ring. You need to put these contacts which are tangent here. Then I have here a coincident. This coincident is between the midplane of the ball and the midplane of the outer ring. This stops the ball from spinning in the other two directions. So right now, the only thing the ball does, it moves, basically spins about the x-axis, not about y or z, by applying this plane constraint. Then I basically mated the flat piece of the cage with the midplane of the outer ring, so it exactly comes to the center. I made the cage concentric with the outer ring, and finally I made the ball surface concentric with the surface of the cage. So you need to apply all of those. And then I did a pattern to do all of the balls, and then I did a mirror of the cage to get the other side. Okay, and I'm gonna show you that in 1 second, but I want to emphasize what could go wrong, or what was the wrong thing that I saw in those videos. And then I want to explain the relation between the angular velocity of the inner ring if we fix the outer ring and we spin the inner ring, right? So the inner ring is attached to a shaft that is spinning, the outer ring is inside the fixed casing. Is the cage gonna spin with the same RPM as the inner ring does? The answer is no. They are related, and the cage is always spinning slower than the inner ring. And if there is an angle, the relation is modified. But if the inner ring is spinning at, let's say, 100 RPM, the cage always spins slower than that. And that is the mistake that I have seen. So let me show you here how to assemble it very fast. I want to apply those constraints again for you so you can see them. Okay, and then we are going to talk about the relation. So this is the outer ring, right? And now I'm gonna bring the inner ring. I'm gonna bring them one at a time and assemble them. The outer ring brought first, so it's fixed, and I want to keep it fixed. So the first thing I do here is I force these two surfaces to be concentric like that, and then I force these two surfaces to be coincident. Okay, right now the inner ring is good. Now I'm gonna bring the ball here. Okay, so let's bring a ball. Now for the ball, I force this surface of it with the inner ring to be basically contact or tangent in this case. And then you have to apply a tangent between these two as well, because you want to take the fact that this one is fixed. So on one side of it, the contact point doesn't move. On the other side, the contact point moves the same speed as the outer surface of the inner ring. Okay, so if you assume no slipping happens. Okay, so now the ball is in place, and now if you look, the ball only moves inside the raceway. Now the ball not only can spin about the x-axis, as I said, it can also at the moment spins about the y-axis or the z-axis. So you have to take those degrees of freedom away, and for that reason I take a mid-plane of this. Let's say I take, for instance, the right plane of this ball, and I take the right plane of the outer cage, which is fixed, and I force them to be coincident. Okay, so this way, look, you can see that if I show you in the mate, now the ball can only spin about its own x-axis, okay, and you cannot do anything else. And look here, when I move the ball, the inner ring does rotate with it, or if I move the inner ring, the ball does move with it. Now it's not super clear here, but you can see that. Now I'm gonna bring the cage, and then I show you how to assemble the cage. So this is the cage. The first thing I want to do, I force this flat surface of it to be coincident with the midplane of the outer ring here, which is this plane here. Okay, so I made these two coincident and it should sit against it. So make sure it is sitting against it. There we go. Right? Then you need to make it concentric. So here I pick this portion of the arc, and then I can pick this arc and force these to be concentric. There we go. The cage is now exactly in place. Okay. So look at the cage, see what degrees of freedom it can have. All it can do is spin, which is exactly what you want. Now you need to put it in contact with the ball. So I pick this surface, I pick the ball surface, and I make them concentric as well because they are both spherical. Okay, now they are exactly assembled right, and you see that if I move the ball, everything does move with it. So now I just do a pattern. So I get the circular pattern, and I want to pattern the ball, and the axis is the axis of this one here. You can either make the visible the temporary axis and pick that, or you can just pick a round object with that axis. I use equal spacing and 8 here. There we go. The balls are all in place, and then I pick the cage, right? And then I'm gonna mirror this, and the mirror surface is the surface here, and that should give me the other cage. Done. Okay, so this is how you assemble it. Now if you have pins, you can put the pins inside this hole and then do a circular pattern of the pin as well. But for now, I just want to skip the pin, so I want to talk about the angular velocities. Good. So this is how you assemble it. Now let's talk about a simple motion study on this. So here is the same thing. Now I want to show you a motion study. So in this motion study, I applied a motor, and I applied it to the inner surface of the inner ring, as you can see, right? Look, the face is this face here with respect to this object that is fixed and is 10 RPM, as you can see, clockwise, right? So now it should start spinning. Now, is that enough for the motion simulation? No. You need to specify that there is a contact between the ball and the two raceways. If you don't do that, you are not going to get a proper motion analysis. Okay, so here what you need to do, as you can see, let me show you, is the contact. Okay, so you go and click on the contact, and then you pick the ball, and then you pick the inner race, and then you pick the outer race, and now meaning that these objects have contact with each other. Okay, yes, and these are solid bodies. So if you don't do that, you'll see that the inner ring starts to spin, but the ball and the cage barely move, or they don't move at all. But if you put it this way, they should move. So now I go to motion analysis and I let it calculate. Initially, it goes a little bit slow, so they catch up. But once they catch up after 4 or 5 seconds and they become steady, now look, clearly you see that the inner ring is spinning faster than the cage. Look here, you clearly can see that. The cage is never spinning as fast as the inner ring. And that is the wrong thing, as I saw I told you I saw in one of the videos. So in that video, the thing they did, they basically aligned the plane of the cage. Let's say in this case, for instance, this plane of the cage, for instance, let's say this. They aligned the right plane of the cage with the right plane of the inner ring, or in this case, maybe the front plane of it, okay? And they forced them coincident. So when this inner ring was spinning, the cage was spinning the exact same RPM. That is not physically correct, okay? So please don't do that. And here I want to talk a little bit about the formula relating them, and this is from pure rigid body kinematics. So here is the bearing, and this is a side view. You have a d, small d, which is the diameter of the ball, and you have a capital D, which is the distance between center of the ball to center of the ball. In a bearing, this is called the pitch diameter. So if I fix the outer ring is fixed, and the inner ring is spinning with omega I. You know that the cage will also spin with omega cage, and the balls will also spin with omega ball. So what relation exists between omega I, omega C, and omega B? I want to show you that. So if you look at one ball here, just isolate one ball. The top portion of it, which is attached, which is the raceway on the outer ring, is fixed. So this point has 0 velocity. And this point at the bottom of it is, if you say no sliding, no slipping, that has the same speed as the inner ring. And this one is going to be this distance, whatever it is, which is d over 2 times the omega of the inner ring. Okay? So one side of it has this much velocity, one side of it has the other velocity. Okay? And if that's the case, and this object is going with omega of the ball, and this is d over 2, right? And d over 2, then writing a simple kinematics relation would tell you that velocity of one side of it, that is 0, the other one is this. You can find the omega of the B. Omega of the B is going to be the difference between these two velocities divided by the distance. Okay, so in this notation I have an extra thing, and that is velocity of the cage. That is the velocity of this midpoint V of the C. So if you want to relate V of the C to this fixed point, then clearly V of the C is d over 2 times omega of the ball. So omega of the ball is going to be V of C over d over 2, and that 2 comes to the numerator, so you get 2vc divided by d, okay? So this is omega of the ball in terms of velocity of a center of the cage, okay? Then velocity of the inner point is going to be velocity of the cage plus the distance times omega. And this V of the C and omega of the B that you have first, you're going to replace this omega of the B into this formula here. If you do that, this is this whole thing will become a VC. So you basically get VI equals 2 times V of the center, and you know it is correct, right? When a ball has rolling without the slipping, this point is 0, that point is VC, and this point, as you know, moves with 2 VC, which is equal to velocity of the inner point. Okay, so that is obvious. Now, velocity of the inner point, velocity of a point here, this velocity is equal to also what? Velocity of this point. This is equal to this distance times omega of the cage. And what is this distance? This distance is d over 2 minus small d over 2. So I multiply that distance by omega of the inner ring, that is the velocity of the inner ring, okay, and I place it here. So you're gonna get this. Now remember, velocity of the cage can be written as its distance, which is just d over 2 times omega of the cage, okay? So now look at this equality here. These twos would cancel. To find omega c, we divide both sides by a d, and if you do that, you are gonna get this relation. That omega of the cage is 1/2 1 minus d over d times omega I. And clearly you know that this ratio is less than 1, so the whole ratio is less than 1/2. In other words, omega c is less than 1/2 omega of the inner cage. Okay, so if the inner cage is spinning 10 rpm, the cage is not even gonna spin 5 rpm. It's gonna go less than 5 rpm. Okay, and that's what you saw in that simulation, that the cage was not spinning as fast as the inner ring. It should not. But if you force them by making two planes coincident, that is kinematically wrong. Okay, so this is it. Now there are cases where the raceway has an angle. So you can see that the inner and the outer ring, their cut is such that the ball is placed at an angle. In that case, instead of d, you are really using this distance, and this distance is d cosine theta. So instead of that d, you have to use a d cosine theta in the formula, and this is the relation that you will find. Okay? So now you see why the cage is spinning slower than the inner ring. So hopefully this video was useful to you. You learn more about proper way of assembling and some important formula. Thank you so much. I'll see you in the next video.